Good morning. I'm Bhiman Nath, and I would like to welcome you all on behalf of the organizers to the Bangalore Bubbles Conference. For the next 4 days, we'll be discussing various aspects of galactic outflows, superbubbles, star clusters, comic bubble, circumgalactic medium, theoretical, observational, modeling-related aspects, and how they are interrelated and the roles they play in galactic evolution. I feel excited by the fact that so many experts in the field have made time to come here and join in the discussions. Some of you have come to India for the first time, some of you have come from different corners of the country. So welcome to you all. I hope you'll have a pleasant stay and fruitful time in Bangalore. Please don't hesitate to contact any of us in the LOC in case of any problems, confusions, clarifications, local information. And so we have divided the 4 days into 4 main topics of the conference: outflows, circumgalactic medium, superbubbles and star clusters, and the comic bubbles. And each day we'll begin with a set of review talks, a mix of theoretical, observational talks to set the stage for more specific talks after the lunch. At the end of the day, we'll have sort of a discussion. So I hope there will be a lot of questions, and so that we have some idea what to do and the directions that these fields are going to take. And there are also posters, and the poster authors will get a chance to present their work, briefly summarize their work at some point of time. So that's all, and so let me welcome you once again, and let's, without further ado, I would like to, who's here? Okay. So let me invite the chair of the first session, Yuri Shekinov, and let's begin. Thank you.
Thank you, and I'm happy to welcome all us here. And the first talk is by Veilleux, right? Bubbles, Outflows, and the CGM.
Good morning. I should thank the organizer. This is actually, I'm one of the first timer here. I've never been to India before, remarkably. So I'd like to thank Iman and Pratik especially, but all the organizers of this conference for inviting me and really trying to enjoy. I really look forward to these 4 days. Really a wonderful program. Congratulations for putting together a very strong program. So it's remarkable what Google can do for you when you search for bubble and Indian flag. You get a lot of hits, and one of these is this wonderful picture of this stylish Indian flag, and I think it really crystallized many of the ideas that we discussed at this conference, but also what I'll address in this talk. It's clearly a bubble in the center. Here, and driving an outflow along the path of least resistance to, I would say, a disk of galaxy. And this material is ejected out of the disk and deposited into the circumgalactic medium, this saffron and green in this picture. So this is obviously a theoretical picture of the phenomena that are taking place in a galaxy, and one can replace this with one of your favorite bubble. Happens to be the bubble in 1839 as far as I'm concerned, where the scale of this bubble is divided to a parsec, and we see velocities of 1,000 seconds. Back to this object later. But I guess the point I want to make is these objects are not isolated from the environment. One really has to take into account where they live. This outflow will be deposited, some material will be deposited in the galactic medium, but one really has to take into account the entire galaxy ecosystem. And so just to set the picture, and using another of these artistic rendition of the Circumgalactic medium taken from the annual review, recent annual review by Thomas and Jess work, or a picture from Simon Lilly, which is more straightforward, tries to explain what all the gas flows taking place in the galaxy. And so the picture that I want to emphasize here is most of the processes that we're going to be discussing at this conference would be considered in this picture internal processes. And the nomenclature of the closed box model and leaky box model come from the classic paper by Beatrice Tinsley, which really set things up in the 1980s. Those of you who haven't seen it, it really is a must. It's basically a book, and it's one of the classic, and it's strongly recommended. We're using the nomenclature of a closed box model, where basically we're considering a galaxy that is a closed box island universe, not completely isolated, where star formation takes place and gas is exhausted. And that's now often called starvation or strangulation in the modern literature. That was not mentioned. Many of the phenomena we're going to discuss at this conference would fall in that category of leaky box model, where gas flows are involved, gas flows from starbursts, starburst-driven outflows, or AGN-driven outflows, where there are a number of processes that are taking place. I'll back later. But these processes of gas outflow can quench star formation, completely stop it, or it can prevent it, where the gas is ejected but eventually comes back, and it's a more preventive mode, especially when we consider AGN and jets, the radio mode of AGN. But of course, this is not the full picture. There's also aspects that these galaxies live with the outside world, and gas will be falling back into the galaxy. And so we have to consider external and environmental processes. And so gas inflow will have a very strong influence on the evolution of these galaxies. And there will be a balance between gas inflows and gas outflows and star formation. And in the case where the galaxy is really massive, there are processes called Veilleux quenching, where the gas falls into the galaxy and shock, heat, or ionize, and actually prevents star formation. It's another way to prevent star formation without doing anything internally. And then if we consider galaxies in a cluster, we have to consider ram pressure stripping, evaporation, tidal stripping, and harassment. Probably phenomena that probably will not be discussed at this conference, but are important in affecting the galaxy evolution, in which these bubbles or galactic outflows are taking place. So it's something to keep in mind. It really depends on phenomena. It will depend on the environment, it will depend on companions near the galaxy, etc. This is just to set things up. So the plan for today, I'm going to touch on a number of scales. I'll talk a little bit about small scale, the driving mechanism. But I understand Anand will talk quite a bit about that in the third talk this morning, so I'll say a few words. Most of the discussion will be on the galaxy scale, the multi-phase outflow, emphasizing the multi-phase aspects of these outflows. And then I'll say a few words about new results that we're finding on the Circumgalactic medium at high redshift 2 to 5. And then hopefully I'll have time to say a little bit about a few words about JWST and a program that we have that will study galactic outflows for JWST. So let me start with the small scale, the driving mechanism. And this is an expert audience, so just want to set things up, make sure that everybody's on the same page. Talking about injection of energy and momentum radiation to drive these galactic outflows. And there's obviously two types of drivers, starburst and the AGN. And in the case of the simplest case, I would say, of energy conserving phenomena where the supernova, the stellar winds, get the energy from those, gets thermalized and creates a hot bubble. The pressure of the hot bubble at the center of a galaxy is given by this expression. So it's actually a very simple expression. Pressure is proportional to the surface density of star formation. So this is clearly a critical quantity when one wants to understand starburst-driven winds. This is in the energy conserving case. The momentum conserving case is slightly different, but clearly this quantity is also very important. So the star formation rate, surface density, is just star formation rate divided by the area where our star is the radius of projection of the energy. The other thing I want to emphasize, instead of going into great detail, is the fact that quasars are an incredible source of energy, of radiative energy. If one do just a back of the envelope calculation, the black hole mass, and just calculating the total amount of radiative energy that was produced over the lifetime of the growth of a supermassive black hole of the mass of 10 to the 8 solar masses, assuming 0.1 radiative efficiency, you get of order 10 to 61 hertz, which is a lot more than the binding energy of essentially any galaxies that we know today, m sigma square, even if it's sigma of 400 kilometers per second, exceeds that energy. So it's really a huge amount. So I always say in an introductory talk that it's really amazing that we have a supermassive black hole in the Milky Way. It's really remarkable that we are here and not somewhere else being ejected out of the galaxy. Because if somehow the galaxy formation was able to capture that energy, a large fraction of that energy, well, everything would have been blown out. And clearly that's not the case. And so that energy, there's only a certain fraction of that energy that was captured during galaxy formation.
This is over what time scale?
This is over the time scale of the growth of the black hole. Right, so it's just basically from a seed black hole to a black hole of 10 to the 8 solar masses. That would be the radiated energy over the lifetime of the growth of the black hole. Yeah.
Are there any constraints on that efficiency? I mean, it seems like
yes,
that matters.
That's a good question. But 0.1 is a decent number. It varies, depends on the spin of the black hole. And there's some constraint from the fact that from the mass of the black hole mass distribution as a function of time, which is reasonably well known, especially at z of 0. But so there are some constraints, but I would say it's uncertain by a factor of 2 or 3.
I guess it's worth mentioning there's a missing coupling factor.
That's right. So that's the point I want to emphasize here. There's the coupling factor of that radiation. Clearly, it's not 100% because everything would be blown out, and so it clearly has to be small. Otherwise, it would be a huge impact on the galaxy formation. Yeah, that's the point I want to emphasize. We're not including also radio jets here. Talking about radio jets, I showed you this bubble in NGC 13.9. I want to come back to it, given this is my favorite bubble, and this is the conference about bubbles. This is beautiful, spherically symmetric bubble. It's actually a double bubble. I don't emphasize the aspect of it. It's just like the Fermi bubble, but on different scale. It's smaller scale. But the velocity that we measure is 1,000 kilometers per second. And really, we actually see a mushroom cloud. It's the motion of a mushroom cloud where the gas comes up and actually curls around because the velocity at the top are maximum and smaller at the bottom, and we interpret that as literally like an atomic bomb in the galaxy. I once gave this talk at Los Alamos National Lab, and I mentioned and actually put atomic bomb picture. They all did. Oh, and it really related after that. I never got that feedback ever again, so I'm not sure we're going to picture again. But basically, we think that's very simple. But the point I want to make with jets is that we think that jets, even in this object, which is nicely spherically symmetric, we think that there's a VLBI jet. So if we zoom in on this central region at the base of the bubble, there's a VLBI jet on a much smaller scale. It's been expanded by a factor of 200 here, 250. But it's aligned with this region, which has very broad lines, and we think that some of the driving of this bubble is from the jet. It's certainly happening now, whether or not it really did the whole, all the energy injected into the bubble for a long enough time is still uncertain. But clearly the jet is still doing some work here, even in this object, which is nicely strictly symmetric. Yeah.
So I know I interpret differentiation, but the jet is not pointed toward the minor axis of the jet.
That's right. So it's pointed at an axis.
Jet's going this way.
That's right. So what we think is going on is the jet is impacting the ISM. It's depositing its energy there. After that, it becomes more or less spherically symmetric.
So is it obvious that it's driven by the energy of the supermassive black hole, or star formation?
So there's enough energy from the jet, in this case, to drive the bubble. And the current star formation rate seems to be too low to drive the bubble. But what happened 7 years ago when this bubble went off, we don't really know. And so in the papers that are listed there, we're a bit ambiguous because we're not. I mean, the 1994 paper, I was all out and said the starburst would do it because using from the star formation rate directly from the far infrared. But it's contaminated by the AGN, and now we've discovered, we realize that it's a VLBI jet pointing in that direction. So it's a bit ambiguous. But jets don't necessarily create these not beautiful linear outflows. That's the point I wanted to make. If the jet is stopped and the energy is deposited, basically it can be more or less a spherically symmetric outflow and can produce these bubbles, wide angle outflows. Now another type of outflow from AGN is the wind. So a very small scale. We know they exist. In many AGN, they're ubiquitous. Most of the AGN have these winds on accretion disk scale. And this is sort of an artistic rendition. They're detected in the X-ray and in UV, and I think Anand will talk about these in more detail. But I want to emphasize that the new results from X-rays have, I think, convincingly shown that some of the X-ray winds are really quite spectacular. With velocity, many of them have more modest velocity, thousands of kilometers per second. But some of them, I would say a few of them, there are pretty strong evidence that we see a wind that at velocity are relativistic or nearly relativistic, 0.1 up to perhaps 0.3 C. I think the jury is still out, but these so-called ultra-fast winds, I call them ultra-fast winds, people call them UFOs, ultra-fast outflows, and get a lot of public attention. So I don't want to do that. I prefer the ultra-fast winds. But I think if they are indeed confirmed, I would say these detections are 5, depending on how you look at it, 5, 10 signals. So it's still, I think the jury's still out. And I think keep an eye open on them. But it suggests that certainly these winds would be sufficient to drive.
What's the physical size of this?
So they're accretion disk scale. So in RGs, tens RGs, that sort of thing. So it's really, really small. For these very fast winds, the more modest velocity would be hundreds of RGs. And then comes the UV winds, which would be bigger than that. But still, most of them probably are 60 or less, although there are perhaps some exceptions. But this is an example of UV winds you observe with Cox HST, and you see the sort of zero velocity is here, and all these features, very complex feature in various elements here, highly ionized elements, are observed to fly out of the thousands of kilometers per second. And I'm not going to go into the detail because I think that's probably going to be covered later on. But one can really determine the optical depth, the carbon factor of these outflows. And but the main point I want to make is these UV outflows are ubiquitous in EGN, and they're very good potential source of driving the large-scale winds. Basically, the winds or X-ray winds eventually impact the ISM, deposit their energy or transfer their momentum to the ISM to drive these large-scale outflows. But there are seeds in most AGN. In this case, that we're studying nearby quasar, they're 50% or so. Although we're not actually seeing positive correlation with luminosity or black hole properties, which is a bit surprising, but it's still work in progress. So let me talk, the bulk of this presentation is really about galaxy scale. So I want to talk about the multi-phase outflow and draw the general pictures that I'm sure we'll be discussing in much more detail throughout this conference. But the best place, I would say, for this discussion is in the two classic case of galaxy scale outflow and the scale of a few kiloparsecs, as much as 13 kiloparsecs, cap of H alpha. So this is a bit hard to see, but this is from HST to H alpha, and the X-ray, which is basically what we think is the distance that these galactic, especially in this case, which is energy-driven alpha. X-ray is the distance between these large-scale alpha. Notice the star formation rate surface density is larger than one system. So there's quite a bit of energy injected in the ISM of the galaxy to drive this outflow. Now, perhaps the picture you don't know as much, but again, this is H alpha from the ground now, from West Bucket. So the ionized gas, the warm ionized gas, but the molecular gas also is taking place in this outflow. And it's really a picture that is emerging now that whenever a system is gas rich, the cooler gas is also entrained in these outflow. Nature has found a way to drive these molecular gas, entrain them, and to reach fairly large velocity. So this is actually the warm molecular gas from near-infrared data, and it really is the tip of the iceberg. Most of the mass is in the cold molecular gas, the CO here, so a few tens of degree Kelvin, while this is 2,000 degree Kelvin. And the mass in the outflows is very large, very substantial. 25% of the entire molecular gas in M82 is outflowing, based on the Roy paper. Yeah.
Is the molecular gas moving at the same velocity as the X-ray gas?
Well, the X-ray gas, we don't have a direct measure. We don't have any spectral resolution. But if you derive the temperature of the gas, we're talking about very high velocity, several hundred thousand kilometers per second for the X-ray gas. So this is much slower. It's also slower than H alpha. So as you go to cooler and denser gas, it really is slower.
How much slower?
Consistent with the picture we would have with entrainment, where now it's hard to get the molecular gas going. But this is, after the projection, we're talking about hundreds of kilometers.
So less than the escape velocity, though?
Sorry?
Less than the escape velocity.
Less than the escape velocity. Yeah, that's right. And for H alpha as well, although H alpha is different. But the energies involved is substantial. It's similar to that of H alpha. But the velocities are smaller, but the masses are larger. And whenever molecular gas is involved, the dust also comes along. And that's seen with Spitzer, the warm dust, and the cool dust from Herschel. So the dust is also coming along. And the dust-to-gas ratio is roughly galactic in the system. In fact, it's slightly lower than galactic, as expected in a galaxy like M82, which is a bit smaller. So we think that the gas that was in the disk is being entrained in this outflow. It has very similar properties to the gas in the disk, where it started from. The picture from Adam Leroy, also Martini, more recently, is basically this nice and simple picture that we expected, but it's nice to confirm it, where the hot outflow in the middle, there's on the edge, the molecular gas, H alpha, at the interface is being entrained along the flow. The velocity of the molecular gas is lower. As the H2 is ejected out of the galaxy, we think some fraction of it becomes H1. It dissociates as it goes along the flow. But as you mentioned, the velocities are not large enough for this molecular gas and even the neutral gas, H1, to completely escape. So the gas falls back into the calculation. The hot ionized gas, we think, impacts a cap, which is at 13 kiloparsecs in the case of V2. So it's most likely, although the ionized gas is not seen all the way to 13 kiloparsecs, but the impact of the outflow is seen at 13 kiloparsecs. We think at least some of it actually escape, well, not escape, but at least go as far as 13 kiloparsecs in the case of V2. So this is arguably the best case, the best studied case. But it's a northern object. It hasn't been studied with ALMA too far north. NGC 253 is another starburst, essentially the same distance as NED2. But it's in the south, and we can observe it with ALMA, so you can get exquisite data with full gas. And basically, we think that the same picture applies to NGC 253. The contour here is the CO gas. The blue is the X-ray, the hot gas, and the H alpha is in yellow, greenish here. And basically we see the CO gas wrapping around the alpha of HC53 in the same way as what was observed in V2. What's really remarkable is the fact that essentially all motor gas is entrained in the alpha. We see dense gas that have density of 10 to the 4 particle per cubic centimeter being entrained in the alpha. Very large density. They're basically bullets compared with the hot material. So nature is finding a way to entrain this material. And has the same property as the disk it started from. And if you make a cut along this filament from near the plane to outward, so from near the plane to outward, we see a velocity gradient, which can be interpreted as acceleration of the motor gas. So this is a case where really we seem to see spatially resolved the motor gas being entrained and the alpha and perhaps being accelerated. So this is another object where the star-formation rate surface density is large, enough to drive the alpha.
Is there any evidence for AGN in these two systems?
Not in these two.
How different, if we forget about the PLPI jet in the other case, are they very, very similar?
For the AGN.
Yeah, the first thing that
Yeah, the first two cases are very similar. EGN and 253 are very similar. I'll talk about EGN in a moment. When I put in EGN, what happens? I'll talk about that. So this is another case. Hadron galaxy, but in this case, not very active. The star-formation rate surface density is 0.1. So you wouldn't expect, perhaps, that you would see anything particularly exciting going on here. So this is a slow application. But if we look at Herschel, looking at the coal dust, there's a lot of material above the disk of this galaxy. In fact, so this NGC 4631, 85% of the dust, the coal dust, now we're talking about from 70 and 160 micron and other bands, is in the disk, but 15% of the dust is in the halo, as defined in this picture. So something has lifted the coal dust above the disk somehow. And just in this region here, which we call the bubble, 5% of the entire amount of coal dust. So something has lifted the coal dust above the disk. The hint comes from the X-ray. This is the X-ray. And indeed, the X-ray is also elevated. There's what has been called in the past also a bubble, X-ray bubble, above the disk. And so we think it's related. There was an event that took place in NGC 4631 a few million years ago that lifted the dust above the disk. And so looking at the current star formation rate is not always, of course, an indicator of what happened in the past. So we think that the star formation rate has to be elevated by a factor of 2 to be able to lift the material, the amount of material that we see a few million years ago. 1 to 10 million years ago. Hard to know because we don't have the velocity. Right? So we know where it is. If you assume typical velocity, then you can get that sort of time scale.
Population studies.
Yeah, the population study, I mean, there's still star formation going on in the system. It's just very small. And so we don't have the level of high quality spectroscopy in the system where you can get not only the star formation rate, but star formation distance, because it's contaminated with current star formation. But it's a good question. It's hard to do with the Milky Way, our own Milky Way, so it's very hard to do. Question? Yeah.
Do you have any constraint on the fact that the best field survives in this state of environment? It's not
That's a very good question. In fact, it's something we mentioned in the paper, and we hand wave our a little bit to say it can survive. But if it's clumpy a little bit, it's protected and shielded. I think there are many theorists in the crowd. It's part of the discussion actually. How can the dust survive in this environment? How can the molecular gas survive in this environment to begin with? I mean, that's to me is a related question. The clumpiness must have something to do with it, being able to shield it. I just want to mention the last point, the last galaxy, the last star formation galaxy. Another example is a classic case of a wind system in H alpha, but it's a dwarf galaxy, so you don't need a very high star formation rate surface density to drive this material. So this is a star formation rate surface density. And again, this is from Herschel, the cooler dust. More than 50% of the cool dust in this system is outside of the disk. And again, something has ejected it out. We think, it's actually we see H alpha filaments all over the place in the system. Crystal Martin and Sally Louis detected these beautiful filaments that indicates that the starburst-driven wind is taking place in the system. And we think that a lot of the cool dust that we see in the system is also trained. So it really matters not only the star formation rate surface density, but also the type of galaxy we're talking about. In the case of dwarf, of course, it's a lot easier to eject material because the escape velocity is this small. Most of this material is not going to escape the galaxy, but it's going to be deposited on larger scale, perhaps part of the base of the circumgalactic. Now, so this is all star formation. So what happens when you put the AGN in the center of the galaxy? I could talk about the Milky Way, but I think there will be a lot of discussion about that, about the beautiful Fermi bubble. So let me put a real powerful AGN. I'll put a quasar. So looking at the nearest quasar, marking P31, it literally is sort of the archetype of outflow in a system. We see it on small scale, which I don't discuss here, but also on galactic scale. So this is how it looks like in the optical. And if you take basically a high integral field spectroscopy in the system, this is the velocity that we obtained a few years ago with David Ruppke. And everything here is blue shifted. This is sodium feature in absorption. So we're looking at the neutral gas in absorption. So we know if it's blue shifted, we know it's really moving in our direction. And the velocities are several hundred kilometers per second, thousands of kilometers per second. Everything we see here is moving in our direction. So we're looking at this outflow in a face-on fashion. So this is the neutral gas. Again, also the H1, there's a beautiful wings that we detected, was detected actually earlier on as well, but confirmed in this paper, setting to 1,500 kilometers per second. Again, very high velocity. About a few years earlier, Herschel detected molecular gas in this system. Again, moving at 1,000 kilometers per second. So this is molecular gas, OH in this case, but CO is also moving at this sort of velocity, being entrained in the outflow, and somehow surviving the trip on scales of kiloparsecs or so. The OH outflow is on scales of a few hundred parsec, while the CO outflow is resolved actually with interferometry on scales of a kiloparsec. So this mocha gas that moves at 1,000 kilometers per second is seen on scales of kiloparsecs. And then this, all these outflow lives in environment. This is the X-ray, and extended on scale of 60 kiloparsec. It's alpha enriched. There's a lot of nucleosynthesis from type 2 star, type 2 supernova that was ejected out into this nebula, or just came together. Now, it turns out, as mentioned here, the lesson learned at redshift 0 is that these cool gas outflows are actually quite common in gas-rich systems. This is sort of the archetype. Martin 31 is sort of the archetype. This sort of outflows are seen in many systems. Just to summarize the current picture that we have in these objects that have AGN in them, powerful AGN, quasar-like system, in ULARCs and quasar. The majority of them have these outflows. So they cannot be narrow outflow, they have to be wide angle outflow, that means patchy outflow. So you see them in 70% of all systems. You see them in absorption. So again, it's the background. But basically the statistics with CO is now very similar to that also. 70% of the system that these move out. From Herschel, we determined that the average velocity is 200 kilometers per second of these mocha outflows, but the maximum outflow is 1,000 kilometers per second. Some of the mocha gas is moving at 1,000 kilometers per second. Typical size is a few kiloparsecs, although we detected a system recently that extended to 10 kiloparsecs in CO. The mass outflow rates are wide range and scales basically with the infraluminosity rate, EGN luminosity. In the most extreme case is 1,000 solar masses per year on scale of kiloparsec. So that implies depletion timescales are very short, less than 100 years, 10 years in ULARCs. The momentum injection rate, again, broad range, in the most extreme case, is much larger than the radiation pressure, LIR over C in the system. So we think that in the most extreme case, these outflows are energy-driven, not momentum. They're not driven by the radiation pressure. But there's plenty of energy, as I tried to emphasize at the beginning. AGN, whenever you have an AGN, or even very actively star-forming starbursts, you have a lot of energy, and the kinetic energy I should have mentioned here. This is the kinetic energy is less than 50% of the radiative energy. So there's plenty of energy to drive it, as long as you do it in an energy-conserving way, energy-driven way rather than momentum-driven way. We think that whenever there's a starburst and an AGN at the same time, both of them work together. They don't work against each other. So there's trends with star formation rate and AGN luminosity where the action is combined. And this is a couple of examples here. Velocity of outflow versus LEGN. There's a trend of larger velocity of outflow as the AGN luminosity increases. But there are exceptions, like this guy here, which you cannot see the name, but basically it's a case where the starburst is actually very concentrated, and we think is driving the outflow. So it really is a two-dimensional parameter space of L starburst and LEGN driving the outflow, working together. And that was shown recently by a paper by Bush, where this is the mass outflow rate versus a combination of AGN, luminosity, and star formation rate. So there's a beautiful correlation. This is looking at the CO outflow. So what is the outflow rate? The outflow rate in this system all the way to 1,000 solar masses in the extreme cases. How is it determined? Yeah, well, there's different methods. And so OH and CO. So in all cases, there's in OH, for instance, we have multiple transition, and we can derive the location of where it happens. So the moment we have a location, we can derive the mass outflow rates. Now, there's an assumption about the OH to H2 ratio, and but more recently, I didn't list it here, by a paper by Myra Stone, a student in Maryland, where we actually confirmed that the OH over H ratio using up-to-date differences that are seen in Spitzer are what we assume in this paper. We think that we're not too far off in these papers we publish OH. The CO is the same thing, but it's spatially resolved so that at least the location is better determined. And then the CO to H2 ratio assumption. And all these numbers, all these mass outflow rates assume the lowest value possible, Euler-like or even less than that. Okay, so 3. So we're using conservative number for the mass outflow rates. So we think they're uncertain, but I think they're conservative assumptions. But I think you raise a good question. One has to be a little careful about these numbers. They're uncertain. But at least we came from 2 different directions. Even the cilium also method gives numbers that were similar to that, which is a third way of doing it. And they're consistent numbers. Just want to mention that these correlation with LEGN also continue at higher redshift when we look at more luminous quasars. So this is there's a lot of literature on this, but basically it's the kinetic energy of the outflow versus LEGN, but not including the high redshift AGN, more luminous AGN, and you still have the correlation between kinetic energy and the LEGN. This is true also in flux, by the way, redshift dependence here. But these outflow can be driven with a fraction of the volumetric luminosity of the AGN. So there's plenty of energy again to drive these outflows. The most extreme case at high redshift for quasars is this one, where carbon-2, this is observed with ALMA, carbon-2 has been observed on scales of 20 kiloparsecs, 30 kiloparsecs. So it's basically the CGM scale at these redshift. This is redshift 6, extending to 30 kiloparsecs. And these various blobs here are very broad, are interpreted as outflowing out of this system. Integrating the mass outflow rates blob by blob, adding them up, they determine a mass outflow rate of 1400 solar masses per year. But again, the energy is, the kinetic energy is relatively small compared with this very powerful quasar. There's, again, enough energy to drive this model. Yeah.
Just wondering the sort of correlation you're showing on the previous page with the LAGN versus the kinetic energy of the outflow on the power. So, I mean, you started off by mentioning that galaxies are in danger in general if a large fraction of the accretion power to massive black holes is somehow tapped. So, is there a what is it? This must be saying something to make these things consistent. This is saying something about the coupling.
Yeah, the coupling. So this is the coupling of the current agent that we're observing that is active now, and it's of order, a few percent. But, if you look at, there's quite a bit of scatter here, but if you assume about 1%.
But the coupling that you required from the first...
The coupling that is required, that would be the integrated coupling from the very beginning when it was growing. It started perhaps as a seed black hole, very early in the earth, and grew to be 10 to the 8 solar masses.
So that there has to be a mode where the black holes are growing a lot without doing this.
Without coupling efficiently with the output. That's right. So we think, my impression would be that the ULORGs and the quasar that I mentioned here, we're talking about very gas-rich system, and so anything that's coming out in terms of energy from the AGN might be captured more efficiently, because there's gas on 4 pi. And if it's momentum, it will capture. If it's energy in the form of a bubble, if you have 4 pi, you're able to capture a large fraction of it to be able to efficiently drive these outflows. But at some point, the moment you you open up that bubble, that 4-pi bubble, it'll be, the coupling will be much less. Especially if it's a hot bubble, it will just escape. Then the outflow just basically die. That's what that makes expect. So if you're looking at a quasar at the right time, like these infrared quasars and Veilleux, I think we're looking at that at the right time, where the coupling is efficient. But whenever it's much more optically selected or UV selected quasar, they're less gas rich, and we still see outflows in O3, for instance. So actually, many of these warm ionized outflows are from O3. They're still coupling. They're not quite as good as the case of infrared.
These outflows obviously are not resolved in hand. So there must be the assumption of the radius, which is they somehow equate the velocity to the escape velocity.
Now, many of them, whoops, I really jumped. Now, some of them, I forget actually if this wish survey are resolved, but we're now at the stage where we're starting to resolve these redshift quasars, where you see the nebula around O3, and you're actually able to measure the velocity field to first order.
These are O3 outflows?
Yes, these are O3 outflows. Yeah, this is for the warm ionized outflows.
Well, try to make I think there's another point I'm trying to make.
Sure.
There are points there with no error bars, and yet the uncertainties in the kinetic power are very large.
Yeah, this is a wish paper, and so they didn't put the error bars.
Right.
Clearly the error bars.
Right. But in general, for all these measurements, the error bars.
Yeah, because it depends on the density, and the density is not always well determined. I mean, there's ways to do it to constrain the density, but at redshift 2, it's very hard. So there are errors. I mean, it's a log plot, right? It's pretty large error bars too. I agree. So this is where JWST will really help. So I'll come back to that. Let's see. Okay, let me talk about the CGM. I promised I would do that, just to flash a few new results. There's going to be a lot of discussion about the CGM. This is a 3-panel summary of the CGM, the fact that galaxies are surrounded by these large, metal-rich, dusty halos that contains a lot of metal and dust. But the method that has been used is from using quasars as background, probing nearby galaxies or distant galaxies, middle panel, or directly imaging the CGM. This is a field that is moving very quickly, but that's an example on the right of Lemon Alpha, nebula scales of the CGM. So if I were to summarize that, the current studies of M star, log M star versus redshift, it's a bit complicated plot. So the point I wanted to make, this is perhaps from the COS survey here, at low redshift, COS and COS dwarf, etc., all the surveys from COS, broad range of stellar mass at low redshift. And emission line maps, they have to be bright enough, and so they're a pretty massive system, but redshift all the way to redshift of 3 or 4. But the GRBs, especially the long GRBs that go off in the center of a gas-rich galaxy, are in principle a very good probe also of the GRB. They're very bright, catch them at the right time. So a GRB goes off in this picture, and we're observing them, we'll be able to look at the environment. We know exactly where it is. We know exactly where the host of this object is. After the GRB goes off, we see the host, we can detect the host, we can determine the property of the host. So that's the advantage of GRB. The disadvantage, of course, is that there's going to be contamination from the disk of the galaxy itself. But it will, the line of sight in absorption will contain information about the ISM, but also the CGM. This has been, there's been a number of studies, a few studies, I would say, work. And Andrew, for instance, published a very nice paper in 2008 on that, 7 objects. And so we extended this is a thesis by Pradeep Gatina, who's, I must say, is a product So yeah, he was an undergraduate at IIT Bombay. So we're very glad to have him at Maryland doing a thesis on this CGM using gamma ray burst, using 32 gamma ray bursts, now 32 long gamma ray bursts that in great detail, high spectral resolution. There's many more actually at lower spectral resolution, but these are only the high resolution spectra. So from redshift 2 to 5. And deciding these are the long gamma ray bursts, so they go off. They're associated with massive star explosion. So we know they're in the disk, whatever is a disk of the galaxy dimension 5. So what are the expectation if a gamma ray burst goes off and we have a line of sight to it? Now the absorption along that line of sight will come from the disk, or whatever is a disk, and then the CGM. But this is a very simple toy model. The point that I want to make is the expectation is the ISM will only contribute at a very small velocity, and that's shown here. The red is the absorption, this is column density as a function of velocity. It's really concentrated on the inner 50 kilometers per second, or so, perhaps as much as 100 kilometers per second if we're really generous. And this is just random line of sight, 30 random line of sight to the end. So this is, well, the CGM will contribute a much broader range of velocities. Of course, what we observe, it will be the combination of the two, so it might look something like that in terms of columns. Again, this is a very simple toy model, but the point I want to make is that the ISM contribution to contamination will be on a small velocity scale. If you see anything broad, a lot of it comes from the CGM itself. So just to make the long story short, this is examples of median profile, where the green is the median of all these, in this case, 29 GRBs, 32, and 32. And what's immediately clear is that the low ionization lines, silicon 2, iron 2, are much narrower than the higher ionization line, silicon 4, carbon 4. And the scale here is shown, so 200 plus or minus 200 kilometers per second is shown. Yes?
Do you have any information on post-galaxy kinematics?
Post-galaxy kinematics.
So in other words, do we know whether these are Keplerian-like or sub-Keplerian?
We don't. We have some information on the host galaxy in terms of stellar mass, but we don't have a rotation curve, the expression resolve rotation. These are very difficult, so it's quite difficult. But again, the expectation is that the GRB goes off, and you're not going to sample much of the ISM. Perhaps the inner 50 kilometers per second or so will be the ISM, but anything outside will be the CGM. Yes.
So you can ignore any column which comes from the stellar system itself.
Just stellar system, like the circumverse.
Yeah.
Yeah. So I mean that's part of the discussion, but we think that most of it will be at virtually small velocity. There'll be some exceptional, feature here, but if you take the median, we think that things average out, and that on average, at high velocity, it will be the CGM, and anything that happens near the burst or ISM will be the portion of that profile. Maybe the other slide I want to show is just to drive the point that the high ionization lines are broader than the low ionization lines. So this is a combination of UVES and high res for KEC and X shooter also. So it's basically everything that has been going off for the last few years.
Tracking is done at which redshift? The redshift of absorption line is take the range from.
Yes, it's been quiet. So this is so that's a very important point actually. We think that there's some confusion. Some of the papers that have been published recently. And we use the low ionization line. And we have other profiles like these, but even others. We have 15 lines that are well detected. And So we can determine the redshift. We think we can determine the redshift of these low ionization lines quite nicely because they're all consistent, like the peak. So that's where we. So that's the redshift of where the burst took place. There might be a rotation of the burst, so that's okay. That's the redshift.
And you can comment on the fact that the ionization lines appear to be skewed to the redshift.
Yeah, Andrew actually got something like that as well, based on 7 objects. Sorry. Yeah. And so, I mean, one interpretation of the outflows, right? I didn't say it because, well, it's still a work in progress. But it certainly seems that way. We see it, we see it in other species as well. But the statistics is better given we have 32 objects. We have 06, we have natural fog, etc. All these lines. Statistics is a bit weaker. But yeah, it's intriguing. That's why it fits well within the context. Let me just flash one slide before I talk about JWST. We can do line ratios of all these lines. So this is one example using carbon 4. So basically, carbon 4 divided by low ionization lines. Just to emphasize the fact again that the profiles of the high ionization lines are broader, perhaps skewed, but certainly broader than the profile of the low ionization lines. So it's very similar to what we see at low redshift. Cost. We detect the low ionization lines in the CGM, but the high ionization lines are much stronger. So the metals are already there at redshift 2 to 5. It's already in place at these high redshifts. This is the 06 2. So the statistics are lower. Okay, let me talk about JWST, the last 5 minutes that I have. And there's many things that can be done with JWST. I'm sure many of you have projects in mind. Let me just say the project that I'm involved in, we call it Q3D, Quasar 3D, basically doing IFU spectroscopy, 2-dimensional spectroscopy of quasars over a range of redshift. This is a program that is led by Nico Veilleux as PI, and Nadia Zamkaska as co-PI, and Dave Rucky is also playing a very strong role in this collaboration. The team members. The idea is to, so this is an approved program, DDRS program. The idea is with 27 hours of using the IFU NERSPEC and theory to observe 3 quasars in great detail. Redshift 0.4, 1.6, and 2.9. So a range of redshift to exercise JWST IFU system. The 0.4 should be easy. The 1.6 should be relatively easy. And the 2.9 should be quite challenging. So the point of these DDRS program is to challenge JWST so we can give you information about what can be done with JWST IFU system. We think that these 3 systems, all 3 systems have evidence for outflows at least extended ionized on ground base scale, using AO ground base. The goal of this program is to study the ionized and molecular gas phase in these quasar-driven outflows or nebula, and basically try to be a pathfinder for future study. This is just skimming the surface, just 3 systems. We're having a broad range of systems to give you an idea of what can be done. Again, the other thing I want to emphasize and advertise here is that we're also committed to provide a tool to help you analyze these data. It's really a problem to have a very bright source in the middle of an IFU for JWST. It doesn't quite handle it easily. And we have a tool that we've tested on the ground called IFS Fit, led by Dave Rucky in this paper, and to decompose the PSF, the bright PSF of the remainder of the host galaxy. And it's a very difficult problem when you look at the detail of this. And so by a year or 2 before JWST gets launched, actually just after JWST gets launched, we'll make this powerful new tool, an ASOS tool, available to the community. And so, even if you're not interested in quasar, where you're looking at a system that you want to observe with JWST IFU, and the system has a bright source, which will dominate the central one of the pixels, and you want to remove it, this is the tool you want to use to remove the contamination from the wings of that bright PSA. So if you're interested, come and see me. So I'm probably almost out of time. Let me just summarize. And so I covered quite a bit of ground there, but on the small scale, one thing I want to emphasize is that if quasar were efficient, they would blow away galaxies, but they're not, clearly, because we're here. The critical aspect for starbursts, in my opinion, is self-constrained surface density, or L starburst, and how it's distributed in the galaxy. I didn't discuss about radiation. I'm sure Norman will discuss about that. Momentum-driven winds. I didn't discuss about cosmic rays. I know there's quite a bit of interest about cosmic rays here. I'm sure that will be discussed further. I actually, and I'll put a plug about cosmic rays. We now have an element, an object, Mercury 31 actually, where we actually see the impact of cosmic ray ionization in the lunar gas. So it may not be providing the pressure to drive these outflows, although I think that's still TBD. It's very hard to constrain. But we really think that it's ionizing some of the lunar gas quite efficiently, X-ray connected to shield it. It's favored by Eduardo Menzel and some folks in this here. I talked a little bit about the winds, X-ray and UV winds, their importance. They're ubiquitous in all AGN. So I think that it's an efficient way to get things started, at least for AGN. And that wind will impact the ISM, deposit its energy, or transfer the momentum and drive the large scale outflows today. I spent quite a bit of time on the multi-phase outflow, trying to emphasize that basically all phases of the outflows are taking place. And what's remarkable to me, I think to many people, is the fact that we're seeing bullets of density of 10 to the 4 particles per cubic centimeter being accelerated at 1,000 kilometers per second. Now you might argue that the mass alpha rates are uncertain, and I completely agree with that. But the velocities are measured. We can't avoid that. And we see molecular gas flying at 1,000 kilometers per second and scale it to a parsec. That's quite remarkable. I mentioned a few new constraints about the CGN. Using gamma reverse, it seems like the CGN we see today was in place. Redshift 2, 3, or 4, perhaps 5. And then finally, come and see me if you're interested to know a bit about JWST, what can be done, and also the tools that we're putting together. And feedback to me is what you would need to make sure that our tool that we're putting together is appropriate for your purpose. Stop here. Thanks.
So very quick questions.
So on the molecular outflows, what is your understanding of how far does it go? Because we don't see a lot of molecules back on the surface.
On scales of 100 kilometers.
50 kilometers.
Yeah, I think.
So, in some sense, then they might not play a big role in that.
Yeah, I think that's a good point. We're clearly limited by sensitivity in the current study with DRAM. And now that we have ALMA, we can now put new constraints. And so the system that we observed recently, that we published in 2017, we detect the outflow, I think it's the CO gas, in the wings, so the outflow, on a scale of 10 kiloparsecs, perhaps 15. And that was almost a snapshot for alpha. It was 4 hours. Did that for 4 hours. So it was really not very deep. Clearly there's a need. It's hard to sell that idea, but just to observe the same object, go deeper by a factor 2 or 3 and see if it extends further. So I think the extent, in my opinion, is still TBD. I don't think it's going to extend 50 kiloparsecs. Probably the rate you mentioned. I think that was a very good number. Eventually, this bunker gas will dissociate. It will mix in. It'll probably become ionized. but it might become part of the CGM on that sort of scale. So I don't think the outflow system extends that far. Well, the carbon-2 system at redshift 6 that I flashed here extends on 30 kiloparsecs for a redshift 6 galaxy. So that's very large. So we know they're neutral gas. It's not Milky gas, but it's neutral gas. And that's been detected in absorption.
So I'm fascinated by this idea of the joint influence of star formation and AGN in terms of driving winds, and in particular that plot you showed by Veilleux from 2018. I was wondering if anyone has attempted a more kind of empirical scaling of wind, multi-phase wind properties, sort of like a wind BPT diagram. And has anyone attempted this, and what do you think would be the limitations in doing so?
Well, this is sort of the first version of that, right? If I understand.
Well, yeah, but you've got a mass outflow rate and an AGN luminosity, whereas a BPT diagram, you might just be able to look at the line ratios, for instance, in the different gas phases, and, theoretically at least, determine to what extent it's star forming or AGN.
Well, okay, we should talk. But there's a difference first between the source of the energy, where BPT, I would call it something else. The BPT diagram is a powerful tool. Of course, Spitzer and the near-infrared and mid-infrared line are also very powerful to distinguish between starburst and AGN. And many of the constraints I put in here, the axis of AGN luminosity and starburst luminosity, use those diagrams. Not so much the output line, but the mid-infrared line from Spitzer. And JWST in the near future to determine the energy source. Now, then to your question, using the line ratio in the wind itself, we have information about that, of course. And some objects, like MED2, we know that along the axis of the two stellar cluster, they're dominated by the OB photonization. You go further out, it becomes more shock-like. There's clearly beautiful channels of radiation that comes out of the stellar cluster and ionized material that's dominating the ionization. But further out, there's more shock-like. In the bubble that I showed you, this one here, it's completely dominated by shocks. The velocities are much larger, and so there's a correlation. It will depend on the phase of the outflow. Also, the velocity of the outflow will determine the type of line ratio. And so I think it will tell you a lot about phenomena going on that we correlate with the kinematics, but whether or not it's going to become a fundamental plane of collective waves is a story. I think looking at the energy source versus the properties of the outflow, where on one axis you have the energy source like L, AGN, L starburst. Stellar mass also is another parameter, global parameter that they measure pretty easily, versus the property of wind energy. Research. It's starting with, there are a few other papers also that say the wind is bigger than the town. There's a few other papers that argue that, we argued that earlier as well. But with JWST, we'll be able to extend it at high redshift.
Coffee is getting already cold. Thanks